there is a map we hold in our minds, a picture of the universe. It is crowded, glittering, and impossibly vast. We imagine our galaxy, the Milky Way, as a single grain of sand. This grain rests upon a shoreline of billions of other galaxies. An infinite beach stretching out under the light of eternity. This conception of a cosmos teeming with matter is both comforting and correct, but it is also, from our specific vantage point, a profound illusion. We are taught that on the grandest of scales the universe is uniform, that no matter where you travel the view is roughly the same. This foundational idea, the cosmological principle, is the bedrock of modern physics. Yet a startling discovery suggests our immediate neighborhood is anything but typical. Our home, the Milky Way, appears to be floating in an immense ocean of nothingness. Imagine a desert so colossal it would take light 2 billion years to cross it. A profound underdensity in the cosmic web, a colossal bubble of emptiness. This is the scale of the void we inhabit. We are not on that crowded, infinite shoreline of galaxies. We are adrift in a staggering emptiness, a local anomaly of unthinkable proportions. And this one fact, this simple, terrifying detail of our cosmic address changes everything. To understand why our location is so profoundly important, we must first look outwards. For nearly a century, we have known that the fabric of space-time is stretching. Edwin Hubble's momentous observations revealed galaxies fleeing from one another. The farther a galaxy is, the faster it appears to recede. This is the signature of an expanding cosmos born from a singular fiery instant. The rate of this cosmic growth, a number known as the Hubble constant, became a cornerstone. Measuring this value is one of the most vital tasks in all of science. It tells us the age of the universe, its history, and its ultimate fate. Cosmologists developed two primary, incredibly precise methods to calculate this number. One method looks deep into the past to the faint afterglow of the Big Bang. This light, the cosmic microwave background, is a fossil from the infant cosmos. It carries an imprint of the universe's initial conditions and how fast it began to swell. This first technique gives us a picture of the early expansion. From these ancient photons, scientists derive a stately measured rate of growth, a figure that has been refined with exquisite precision by spacecraft like Planck. It is a number built on our understanding of fundamental physics and cosmic evolution, a reliable anchor point, a message from the dawn of time itself. The second method for determining the cosmic expansion rate is more direct. It involves building a cosmic distance ladder, a way of measuring distances to nearby galaxies. Astronomers use specific celestial objects like pulsating stars and brilliant supernovae. These are standard candles objects whose intrinsic brightness is known. By comparing their known luminosity to how dim they appear, we can calculate their distance. Once we know how far away these galaxies are, we can measure their speed. This local present-day measurement gives us a different value for the Hubble constant. And this is where the crisis begins. The two methods, both honed over decades, both yielding precise results, disagree. The answers do not match. It's not a small discrepancy, a simple rounding error. The chasm between the two values is significant, persistent, and deeply troubling. The universe appears to be expanding about 9% faster today than our models predict. This conflict, known as the Hubble Tension, is a crack in the cornerstone of cosmology. It suggests that either our measurements are flawed or our understanding of the universe is fundamentally wrong. For years, scientists have scoured their data for some hidden error. Perhaps the standard candles are not as standard as we believed. Maybe there is some unknown physics influencing the cosmic microwave background. Exotic new particles, strange forms of dark energy, or modifications to gravity have all been proposed. Each solution requires adding new, unproven complexity to our elegant model of the cosmos. But what if the problem is not with the physics, but with our assumption? What if the cosmological principle, the idea of a uniform universe, is the flaw? The assumption holds that our place in the cosmos is not special. It presumes that a measurement taken here is representative of the whole. This elegant simplification makes the mathematics of the universe manageable. Yet the heavens themselves have been hinting that this picture is incomplete. As our telescopes have grown more powerful, they have revealed a stunning celestial architecture. Galaxies are not scattered randomly across the void like dust. They are organized into a breathtaking structure known as the cosmic web. Immense filaments of gas and dark matter stretch for hundreds of millions of light years. These luminous threads are studded with clusters of thousands of galaxies. Where these filaments intersect, they form superclusters, the great metropolises of the cosmos. This structure is beautiful, intricate, and anything but uniform. It is a luminous tapestry woven across the darkness. And between the shimmering threads of this galactic network there are the voids. Staggering expanses of near-total emptiness, cosmic deserts, where matter is scarce. These are the quiet, forgotten spaces of the universe. For a long time they were seen as just part of the overall pattern. Then a team of astronomers led by Amy Barger and Ryan Keenan began to wonder. They were not looking for a solution to the Hubble tension. They were simply trying to create a more accurate map of our galactic surroundings. Using a host of telescopes, they meticulously charted the distribution of galaxies around us. What they found was not a typical region of the cosmic web. Their data pointed to something astonishing. Our own Milky Way galaxy, along with our local group and the Virgo supercluster, exists in a void. Not just any void, but one of the largest ever detected. A region of space dramatically less dense than the cosmic average. They named it the Keenan-Barger and Cowie Void, or KBC Void for short. Its scale is almost beyond human comprehension. 2 billion light-years in diameter. A bubble of relative emptiness containing our entire cosmic history. Inside this vast expanse, the density of matter is significantly lower than outside. We are in a cosmic valley, not a bustling celestial city. This discovery was initially intriguing, a curiosity of cosmic geography. But as the Hubble tension grew more acute, some scientists began to connect the dots. What if our location inside this profound underdensity was the missing piece of the puzzle? The idea is both simple and revolutionary. If we live in a region with less matter, it means we also live in a region with less gravity. The immense superclusters and filaments that form the boundaries of our void have more mass. They exert a stronger gravitational pull than the sparse interior of our cosmic bubble. Imagine a boat floating in the middle of a vast lake. Now picture the water in the center of the lake being slightly less dense than the water at the edges. The denser water at the periphery will exert a subtle pressure, a gentle push. Our galaxy and our entire local group is like that boat. We are being pushed outwards by the colossal structures that surround our void. This creates a local outflow, a cosmic current carrying us away from the center of the emptiness. It is a gravitational tide pulling us toward the denser regions of the universe. This local motion is an extra kick, a velocity superimposed on top of the global expansion of space. It means we are not a stationary observer of the cosmos. We are on a moving platform, and this movement alters our perception. When we measure the recession of nearby galaxies, we see them moving away from us. But part of that apparent speed is not from the universe's expansion alone. It is contaminated by our own local gravitationally induced motion. We are moving away from the center of the void, and the galaxies we are measuring are also being pushed. This collective outflow makes everything in our vicinity seem to be receding faster than it truly is. This effect would neatly explain the Hubble tension. Our local measurement taken from within the void is biased. It gives us a higher, faster value for the Hubble constant. Meanwhile, the measurement from the cosmic microwave background is different. That ancient light provides a snapshot of the entire early universe. It captures the true global average expansion rate, unaffected by our local anomaly. The two numbers disagree because they are measuring two different things. One is the true overarching expansion of the cosmos. The other is a local distorted view from inside a gravitational valley. The conflict was never a crack in our physics. It was a failure to recognize our own peculiar address. If this hypothesis is correct, it resolves the Hubble tension without inventing new physics. We don't need mysterious new particles or forces. We simply need to accept that our cosmic neighborhood is not average. The cosmological principle, while true on the largest possible scales, breaks down locally. Our universe is not a perfectly smooth fluid. It is lumpy, structured, and complex. This realization has staggering implications for our understanding of reality. It forces us to reevaluate our place in the great cosmic story. For centuries, the Copernican principle has guided our thinking. It states that we are not in a special or privileged position. Earth is not the center of the solar system. The Sun is not the center of the galaxy. Our galaxy is just one of billions. But the existence of the KBC Void challenges this cherished notion of mediocrity. Our location is in a very real sense special. Not special in a way that gives humanity a central role, but special in that our environment is statistically rare. We happen to live in one of the universe's great underdensities. And this simple fact has skewed our measurements of the cosmos for decades. It also forces us to reconsider the nature of dark energy. Dark energy is the name we give to the mysterious force causing the cosmic expansion to accelerate. We inferred its existence by observing that distant supernovae were dimmer than expected. This suggested they were farther away than they should be, meaning the expansion had sped up. Our models of this acceleration are based on the assumption of a smooth, uniform universe. But if we are in a void, the local dynamics are far more complicated. The gravitational push from the void's edges could mimic the effects of dark energy. From our perspective inside this bubble, the expansion would naturally appear to be accelerating. The outflow from the void's center adds to the global expansion rate. This creates a local illusion of faster than average acceleration. Some physicists have even proposed that the void could explain most, if not all, of the effects we attribute to dark energy. Perhaps this mysterious force is not a new property of space itself. It could be an emergent phenomenon, a consequence of the lumpy distribution of matter. This is a radical idea, and it is far from proven. The scientific consensus still holds that dark energy is real and permeates all of space. However, the void model provides a compelling alternative framework. It suggests that at least a portion of the observed cosmic acceleration is a local artifact. Our universe might be less strange than we thought. The solution might not lie in exotic new theories. It could be found in a more careful accounting of our own cosmic backyard. Of course, this idea is not without its own challenges and controversies. Confirming the precise size and emptiness of the KBC Void is an immense observational task. It requires mapping the positions of millions of galaxies with painstaking accuracy. Some studies have questioned whether the void is empty enough to produce the required effect. The debate is fierce, pushing the limits of our observational capabilities. Alternative solutions to the Hubble tension continue to be explored. The possibility of new physics of a flaw in the standard model of cosmology remains tantalizing. The universe may yet hold surprises that are even stranger than a colossal void. Science thrives on such disagreements on the creative tension between competing ideas. The Hubble crisis has ignited a golden age of cosmological investigation. Regardless of the final answer, the journey has reshaped our cosmic perspective. We have been forced to confront the intricate structure of our universe, to move beyond the simple, elegant models of a homogeneous cosmos. We now understand that our local environment matters deeply. To understand the whole, we must first comprehend our part. We are residents of a cosmic desert looking out at the distant oases of matter. Our view of the heavens is shaped by the gentle, relentless gravitational tides of this emptiness. The light from distant stars travels for billions of years to reach us. On its journey, it traverses the great filaments and voids of the cosmic web. Its path is bent, and its energy is shifted by the very structure of space-time. To read its message correctly, we must account for the full complexity of that journey. We must map the mountains and valleys of the cosmic landscape. Our quest to measure the universe has turned into a quest to map our home, a home that is not a random point in an endless expanse, but a specific place with its own unique history and properties. This shift in perspective is profound. It is a move away from the abstract and the idealized. It is an embrace of the specific, the local, the contingent. We are not just observers of the universe, we are participants within it. Our observations are colored by our position by the gravitational currents that guide our galaxy. Think back to that image of an infinite glittering shoreline. The discovery of the KBC Void does not erase that picture. The universe is still a vast and crowded place filled with wonders, but it tells us that our particular grain of sand is not on the main beach. We are in a quiet cove, a vast and sheltered bay. From here, the roar of the cosmic ocean sounds different. The waves of expansion appear to be moving faster, the tide seems stronger. For years we tried to reconcile this local sound with the global rhythm. Now we are beginning to understand that it is the acoustics of our own cove that make the difference. We are learning the song of our own specific place in the darkness. This journey into the void is a story of humility. It reminds us that our assumptions, no matter how elegant, must be tested against reality. The universe is not obligated to be simple for our convenience. Its true nature is often more intricate, more textured, and more surprising than we imagine. The great cosmic web, with its brilliant filaments and deep voids, is a testament to this complexity. We live in a remarkable time, a moment when our maps of the cosmos are being redrawn. The empty spaces once ignored are now revealing themselves as crucial actors in the cosmic drama. They are not just the absence of matter. They are a fundamental part of the universe's structure and evolution. And our own void, the KBC, may hold the key to one of the deepest mysteries in science. So the next time you look up at the night sky, at the scattered points of light, remember the darkness. Remember the immense, unseen emptiness that separates us from the rest. This is the defining feature of our cosmic neighborhood, a 2 billion light-year expanse of relative nothingness that has shaped our view of everything. We are children of the void, and we are only just beginning to understand what that means.